In section 2.6, we're going to look at graphs of basic functions, discuss continuity, the identity squaring and cubing functions, the square root and cube root functions, the absolute function, piecewise functions, and finally the relation x equals y squared. A function is continuous over an interval of its domain if its hand-drawn graph over interval can be sketched without lifting the pencil from the paper. And the key word is without lifting the pencil. So if I sketch something without lifting the pencil, it is a continuous function. Example 1. Describe the intervals of continuity for each function. This is a parabola that we can sketch by drawing it from left to right, and we will never have to lift our pencil as we do it. So this is a continuous function that is continuous everywhere. So from negative infinity to infinity is the interval of continuity. Describe the intervals of continuity for each function. In this graph, it is different because we have a gap in our graph. This gap is known as a hole. It is a spot where there's a jump in the graph. So we have that the function is continuous from negative 3 to 3 union 3 to infinity because we have a hole at x equals 3. The identity function is defined as f of x equals x. If I plug in a negative 2, it gives me back negative 2. If I plug in a negative 1, it gives us 1. If we plug in a 0, we get a 0. Plug in a 1, get a 1. And plug in a 2, we get a 2. So it's known as the identity function because whatever we plug in, we get back out. If I were to plot negative 2, comma, negative 2, negative 1, 0, 0, 1, 1, and 2, 2, we get a graph that is a line. F of x equals x is a line. It has its domain running from negative infinity to infinity, and the range is also the same, negative infinity to infinity. F of x is increasing on its entire domain from negative infinity to infinity. It is also continuous on its entire domain, negative infinity to infinity. The squaring function is f of x equals x squared. This graph is essentially a parabola. If I plug in negative 2, I have to square it, which gives us positive 4. Negative 1 squared gives us 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. So let's plot the points. Negative 2 comma 4. Negative 1, 1. 0, 0. 1, 1. 2, 4 gives us a parabola with that nice U shape. It decreases from the left side to the vertex, so it decreases from negative infinity to 0, and then it starts increasing from 0 to infinity. It is continuous everywhere. I never have to lift my pencil. It is continuous from negative infinity to infinity. For the cubic function, it's defined as f of x equals x cubed. If I plug in negative 2, cubing it yields negative 8. Negative 1 cubed yields negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed gives us 8. Negative 2 comma 8 is a point down here. Negative 2 comma 8 is plotted. Negative 1 is here. 0, 0 is the origin. 1, 1. and 2, 8 yield our graph. It is a function that is continuous everywhere. It increases on its entire domain from negative infinity to infinity, and it is also continuous on the same interval from negative infinity to infinity. For the square root function, we are very careful of what we select. On the left side, we select points that are very easy to calculate when I take the square root. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4. I select these easy values because I know that when I square root them, I get a nice whole number. The domain is from 0 to infinity. It goes to the left 0, it goes to the right forever. The range is 0, it goes down to 0, and it goes up forever, so the range is from 0 to infinity. It increases on its entire domain, or from 0 to infinity. Notice we use a square bracket because it's included in the graph. 0, 0 is included. It is continuous on its entire domain from 0 to infinity. For the cube root function, it's defined as f of x equals the cube root of x. We're going to again pick values that are easy to calculate the cube root of. The cube root of negative 8 is negative 2. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. And cube root of 8 is just 2. We'll plot the points, negative 8, comma, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, comma, 2. So it's a good idea to learn these graphs. Make sure you make a table and then plot the points in the graph so you know how to do it. It increases on its entire domain from left to right, from negative infinity to infinity, and it is also continuous from negative infinity to infinity. For the absolute value function, it is defined as f of x equals the absolute value of x. So we're just going to plug in negative 2. The absolute value of negative 2 is 2. Absolute value of negative 1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 1 is 1. Absolute value of 1 is 1. Absolute value of 2 is 2. And we'll start by plotting the points negative 2, comma 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. So we have a V shape for the absolute value function. It decreases from negative infinity to 0, and it increases from 0 to infinity. And it is continuous everywhere from negative infinity to infinity. Example 2, we're going to graph a piecewise function defined as negative 2x plus 5 if x is less than or equal to 2, and x plus 1 if x is greater than 2. We'll try part A first. Now, in order to do part A, it's easy to start by plotting points. So I'll plot points that are to the left of x equal to 2. So I'll pick x equals 0, something very easy to plug in. Negative 2 times 0 plus 5 gives me 5. So I'll plot that point first. 0, comma 5. And I know that negative 2x plus 5 is a line, so I'll continue in that way. We'll plot some more points. Let's pick x equals to 2. So negative 2 times 2 plus 5 gives us negative 4 plus 5, which is 1. So we'll plot 2, comma 1 on the graph and then draw our line So the first part of the graph is fairly easy, it's just a straight line. For the second graph, it's x plus 1 if x is greater than 2. If x is greater than 2, I will still use x equals 2, but I have to realize this is not included in the second graph. So we'll plug in a 2. 2 plus 1 gives us 3. So we'll plot the point 2, 3, but remember it's not included, so that's why we have an open circle here. It is not included. Then we'll pick other points to the right side. Let's say x equals 4. That's an easy point to calculate. 4 plus 1 gives us 5. And we have the point 4, 5 is here. And I know x plus 1 is also a line, so we really only need 2 points, and that completes our graph. If you look at it carefully, it is continuous from negative infinity to 2. I'm going to use a bracket because it includes 2. And we're going to say it's also continuous from 2 to infinity. In part B, notice that we are going to graph a line 2x plus 3. So I only need 2 points for that one. And the second one is parabola. I know it's facing down because of that negative. So we'll need probably 3 points for that graph to make sure we have that nice U shape. Let's plug in some values. In the first case, we want to have values of x that are less than or equal to 0. I'll pick negative 3 as our first point. X equals negative 3. 2 times negative 3 plus 3 gives us negative 6 plus 3, which is negative 3. So when we plot negative 3, that value goes down to negative 3. So that's our very first point. I need another point. Let's say x equals 0. I like to pick the endpoints because it's easy to use, and it's included in this equation. So let's use x equals 0. 2 times 0 plus 3 gives us 3. And so we know 0, 3 is on the graph. And then we'll sketch our line. For the parabola, we know it faces down. I am going to select x equals 0, even though it is not part of the parabola. I need to graph it just to make sure there's no gaps, like the previous example. But I know this is not included. Let's plug in negative 0, square it, and add 3 to it. We get the value of 3. So we'll plot 0, 3. But remember, if this was not filled in by the previous graph, we would leave it as an open circle. But in this case, it was filled in by the previous graph, so we don't need it. Let's try x equals 1. Negative 1 squared plus 3 is equal to negative 1 plus 3, which is just 2. So we plug in 1 into the graph, 1, 2, and you get this point here. Let's test another point. Let's say x equals 2. Negative 2 actually squared plus 3 gives us negative 4 plus 3, or negative 1. So we'll graph 2, negative 1, and you can see that we do get a parabola that's starting to curve down in our graph. This graph is actually continuous from negative infinity to infinity. There's actually no gaps because our piecewise function fills in that circle we had earlier. The greatest integer function is defined with this symbol. It looks like a double set of brackets over each other. F of x equals the greatest integer function x if every pair of real number x with the greatest integer that is less than or equal to x. Again, the greatest integer function f of x is going to pair a real number x with an integer that's equal to that or less. The greatest integer f of x. Its domain is defined from negative infinity to infinity, and its range is just integers -3, -2, -1, 0, 1, 2, 3, and so on in either direction. So let's plug in values and see what this function actually looks like. If I plug in -2, the greatest integer that's equal to this, well, that's -2. If we plug in -1.5, the greatest integer that's equal to this or less is -2. So remember, we're looking for an integer that's equal to this number or less. We want to go to -2 because that's actually less than -1.5. If I plug in a -0.99, the greatest integer that's equal to this is actually -1. It is less than -0.99. If I plug in a 0, it's going to give us an output of 0. Plug in 0.001, it actually gives us an output of 0. The greatest integer that's equal to 0.001 or less is 0. If I plug in a 3, it's going to give us a 3. And if I plug in 3.99, it actually gives us 3. So let's look at our graph. -2, 2, we have a point. -1.5, comma, -2. It's going to give us horizontal line. -0.99, it jumps back up to here. -0.99, comma, -1. It gives us a point down here. And so it's going to form this staircase pattern. 0, comma, 0. It's going to give us a point up here. 0.001 is a point down here. 3, it's going to give us a point at 3. 3.99 gives us a point still at 3 until it jumps to 4. Then it goes to the next value up. Example 3, we want to graph the greatest integer function, 1/2 x plus 1. In order to do this problem, it's really easy to select random points and plot those to see the shape of the graph. So I made a list of random points and we'll select these values to plot on our graph. We'll start by using x equals to 0. So the greatest integer function of 1/2 times 0 plus 1 is going to give us the greatest integer function of just 1, and that is equal to 1. Plug in a 1. Now let's try 1/2. The greatest integer function of 1/2 times 1/2 plus 1 is going to yield 1.25. And the greatest integer is going to make this into a value of 1. Let's try to plug in a 1. 1/2 times 1 plus 1 gives us a value of 1.5, and the greatest integer of that or less is 1. So it seems like we're getting 1 consistently. Let's continue. 3/2 now. We'll plug in 1/2 times 3/2 plus 1. That's going to give us 1.75, and the greatest integer that's equal to this or less is actually 1 still, so we're going to get 1 again. Let's plug in a 2. 1/2 times 2 plus 1. 1/2 times 2 is 1. 1 plus 1 gives us a greatest integer of 2, which is 2. It gives us a 2. Let's plug in a 3. 1/2 times 3 plus 1 yields 3/2 plus 1, which gives me a value of 2.5. So this yields 2 when we plug into the greatest integer function. If I plug in a 4, 1/2 times 4 plus 1 gives us 1/2 times 4, which is 2. 2 plus 1 gives us 3. So this changes to 3. We'll plug in -1, the greatest integer of 1/2 times -1 plus 1 is going to yield -1/2 plus 1, or simply the greatest integer of 0.5. The greatest integer that's equal to this or less is 0. So when we plug in -1, we get a 0. Let's plug in a -2 now. 1/2 times -2 plus 1 yields -2 times 1/2 is actually just -1. -1 plus 1 gives us a value of 0. So the greatest integer that's equal to 0 or less is 0. And we'll try one more value just to see what our graph looks like. -3. 1/2 times -3 plus 1 yields, let's see, 1/2 times -3 is -1.5. -1.5 plus 1 is equal to -0.5. And if I take the greatest integer that's equal to this or less, we get a value of -1. The ordered pairs in the table suggest the graph shown. The domain is from -infinity to infinity, and the range is the integers. Here's the graph, and we start by plotting the points we have here.